Hello folks. So in today's video we will create a very simple particle life simulator like this one. So here we have some small particles and the particles interact differently with each other. So for example, all particles are attracted to each other of the same kind. So red attracted to red, yellow to yellow, green to green. But at a very close distance they will repel each other. And on the other hand, the yellow particles will be attracted to red, but the red will repel. And something very interesting rules like this one. And by doing the simulation, I have come across something like this. And as you can see, it looks like some cell-like structure is trying to form over here. It's not perfect, but it's going there. And yeah, this is not something that I have planned. It is only by writing the code I got to see something like this. And I got the inspiration of this video from Digital Genius. And this is a video where he has discussed on this idea that we can add a lot of particles with something like an interaction matrix. And using some very simple attraction rules, we can actually see how from very simple particles, something more like life that has complex behavior may try to emerge. So, for example, with simple rules, so particles are interacting in an interesting way. And although this is not live, this is not conscious, but yeah, we can throw more and more rules and more things over this, and it will resemble something like this. So we have one computer, and we are doing this. Maybe God has a very powerful computer, and he is simulating the whole universe like this one. So anyway, that's it for this, folks, and let's see you in VS Code soon. So I'm at my VS Code, and I have already created one index.html file. I will create the boilerplate, and I will rename these to cells. I will also give some styles to our body. The background color will be black, and to our canvas, which is not yet created but will be created soon, I want to give a border of 2px solid white. In the body section, I will create the canvas and I will connect with my script.js file. Now inside my script.js, first things first, I want to initialize the canvas document, not get, query selector canvas. Then I want to create a context. So canvas dot get context 2D to draw in our canvas. And then we also want to give some dimensions to our canvas. So for example, canvas dot width, I want it to be 500, and canvas dot height, I want 500 again. Now in my index.html file, I will click on the go live, and let's see what we have now. So we have one very beautiful looking canvas, and this is where we will simulate ourselves. So let's get back to our script.js file, and let's see what we need over here. So first of all, I will create a class called particle, and here I will create the constructor. The particle needs one x position, a y position, and also a color, and accordingly I will keep these things. So first of all, the position x will be the same as x, then this dot y is y. This is something that we will pass, and then this dot color will be the color that we are passing. Now what I want is I want the colors, but I also want the colors to be indexed. So for example, red will be 0, yellow will be, let's say, 1, green will be 2, something like that. So although there are other ways to find this thing out, for now I want to pass the color index also, and I want this dot color index to be the color index. It looks a little bit stupid, but yeah, for now just bear with me. And then this dot radius, for now let's keep it 5. And then we also need to specify the velocity. For now it can be 0, and in the y direction also this is 0. And then we also would like to have some max velocity, so this is the maximum velocity that it will reach. Let's give it to 3. I don't know, maybe we'll decrease it later. Then let's do one acceleration or force, whatever you might call. So this will be again 0 0 for now. Now we have one circular particle. Now we have to draw it. So here I will pass the ctx. So ctx dot begin path, and then we also have to close ctx dot close path. And inside we are drawing a circle, so we will do ctx dot arc this dot x, this dot y, with the radius whatever we have, and we need to draw a full circle. So math dot pi times 2. Let's also give the color. So ctx dot fill style will be this dot color, and then ctx dot fill. Now we also need to update, because drawing is only drawing once. So in the update for now, we will do the this dot draw and we'll pass the ctx. Now gradually we'll see how we can do other things also, like updating the position and other things. So now we don't have any particles. So let's create some particles. So for now it will be an empty array. And then what we want to do is we want to push in some particles. So we will do for let I equals to 0 and I should be less than, let's say I want 100 particles. So I plus plus 100 could be too much, but I think we can handle it. And here, what we need to do, we will simply do particles dot push, and inside we will push a new particle, and it wants four parameters: x, y, color, and color index. So we have to create the x, y. So x will be some maths dot random. This will generate something between 0 and 1. So we will multiply it times width. And then so similarly, we will have the y, and instead we will multiply with the height. Now inside the particle, we will pass x, y. The first particle will be red and the index will be 0. Here we can have a rule, or we can simply write something like, not here. So 0 will be red, then 1 will be yellow. We may not go up to 2 now. I mean to say in this video, but yeah, we can just keep it as it is for now. And let's say 4 will be orange, and let's say 5 will be white. Anyway, whatever, we can change these things later, but this is something that we will keep for now. Let me create, let's keep me, let's just keep it at the top for now. Yeah. Okay. So this is how we are pushing the particles, but that's not all. We have to animate. So we will create a function called animate. Inside we will keep the request animation frame animate, and outside we will call the animate. And let's see what we have now. We don't have anything, and that's a little bit strange why we don't have anything. um, inside the animate function, we are only doing animate, we are not doing anything else. What we need to do here is loop through all of our particles and draw them one by one. So what I will do is for let I1 equals to 0. Why I1? Because we may need a nested loop also, and I will, instead of doing ij, I am doing I1 and I2, something like this. So we will loop up to particles dot length and then I1 plus plus. And inside what I want to do is P1. Now, what is P1? So P1 is something that we have to create over here. So P1 is nothing but my particles of index I1. So P1 dot update, and here I will pass a CTX. Let's see. Yeah, so we have a lot of particles, but the particles look a little bit ugly. If you can see, the edges, I mean, circles don't have edges. If I just give a bigger radius, 10 for now, you will see how ugly they are looking. Yeah, it's ugly. And that is because it's repeatedly being drawn on top of each other. And so this ugly look comes. We can simply resolve it by doing a clear rect. We have done this thing so many times, I'm sure. You all know that. So canvas dot width and canvas dot height. Now we have beautiful looking particles. And let me just make it 5 only. We don't need a 10. Yeah, good, very good. Now, what do we want to do? We want the particles to have some speed, and we want the particles to travel, and we also want the particles to interact. We want many things. Now, for doing the interaction, we will need few more things also. So we will need a function called distance. This will find out the distance between two particles, let's say P1 and P2. This is something that we will need. And we will also need one more function, and that is called force. This is also taking two particles, and it will calculate the force. So what do we want to do over here? So here, inside the animate function, we have one for loop that will loop through all the particles once. Now to find out the interaction between two particles here, as I've said, we have to create a nested loop. So here, let I2 equals to 0. I2 is less than particles dot length and I2 plus plus. So it is a nested loop. Here we can write interaction between particles. Now here, what I want to check first of all is I1 and I2 should not be equal, because if they are equal, they are the same particle and we don't need to check anything. We will simply to continue. And after that, we have to find out what is the force, what is this, what is that, etc., etc. So we will take P2. This is nothing but particles of index I2. And then, first of all, we want to get the distance. So distance will come from the distance function. We will pass the P1 and P2. And then we want to check the force. So let it be F. This should once again be P1 and P2. So this is something that we will have to write. Now, let's say if the particles are too close, I don't want them to interact. I want them to, I don't want them to attract each other. I want them to repel instead. And if the particles are at a larger distance, then I want them to, attract each other. So first of all, what we have to check is the distance, whatever. Anyway, we'll do that, but let's first write these two functions. This is more important for now. So how can we calculate the two distances? It's a simple coordinate geometry. We will have an x distance. This is nothing but p2 dot x minus p1 dot x. This can be positive or negative. Similarly, we will have a y distance. This is once again p2 dot y minus p1 dot y. Then we will have a square distance. So square distance is what? This is nothing but x distance into x distance plus y distance into y distance. And then we will have our real distance. So let it be dist, and this will be as the square root of our square distance. So square distance, and we want to return an object that will contain all of these things. We want all. Only distance is not enough. Other things will also come in handy. So yeah, this is all that we want. And now for the force, what we need to have. So first of all, we want to get all of these distances because it will be required to calculate the force. So here we will simply take the x distance, y distance, then square distance and distance from my distance. So we want to call the distance over here and pass the P1 and P2. Yeah, and we are simply destructuring the response. So what will be the total force? So uh, we have a formula that Newton gave us, that is m1 m2 by r square um, g multiplied by g. So this is the gravitational force between two particles or two planets or two bodies. Now we are not taking any mass. Let's assume the mass to be 1. So in that case, m1 m2 will be 1. And what is the g? The g is actually very important. It will determine the interaction, like how strong or weak the interaction between them is. Let's assume the g to be 10, and I want to divide by r square. R is the distance. So here the distance is our distance, and it says distance square. So this is actually our square distance. So this is what we are doing now. And then we also want to get the force in the x direction and y direction, because that is how we will add that. And what is this? This is nothing but x distance divided by distance. And this can be again positive or negative, times force. And similarly, the force x, this is force x, and force y will be y distance by distance times force. And then we will again return all of these things. So we will return force x, then force y, and also the force. Yeah, so we have everything. Now let's see how we can create some sort of an interaction. So we are getting the distance here and we are also getting the force. And now let's do some smart things. So first of all, we will check if the dist, that is the absolute distance, if it is very close. Consider the very close to be 5 times the radius. So radius times 5. So basically, if the absolute value of the radius is 3, no, it is 5 right now. So if it is within 25, if two particles are within 25, what I want is I want the force to be negative. So I want a repulsive force. So what I can do here is something like fx equals to we can do fx minus My I have the force F dot force X. We can also do it minus equals to, and this times 3. And Fy equals to, we can write minus equals to F dot force Y times 3. Now, why we are doing a times 3? Because we want the repulsive force to be much, much stronger than whatever we are getting. So we are getting a force, this force, 10 by square distance. And when the two particles are very close, there will be a repulsion, but I want the repulsion to be 3 times stronger. So that is why we are writing this thing. Now, this is kind of weird. Physics doesn't work in this way, but these are living particles, right? These are living cells or something like that. So we can definitely do this thing. Now, we don't have the fx and fy. We don't have it yet. So it will definitely throw an error. So what I want is I want to first of all declare that. So after the p1 dot update, I want to declare fx to be 0. This is the aggregate of total force towards x for the particle p1. And the fy will also be 0. And after my for loop, I want the fx and fy to be updated. So p1 also has an fx. This will be the new fx, and p2 also, not p2 actually, p1 also has an fy, and I want this to be updated. So I'm initializing it to 0. And now let's say that all the particles are very close. There will be a strong repulsive force, and it is coming here. It is taking all of these things, distance, whatever, whatever, and it is. So we have a highly negative Fi. And then what will happen is the new Fi will be assigned here, Fx and Fi, and it will be updated in the particle. So that is what I want. But right now, it will not do anything actually, because it is only changing these numbers, but it is not really changing the location of the particle. So that is something we need to do now. Um, we have to modify the update function. So in the update function, what we want to do is first of all, the Vx is a velocity and Fx is a force or acceleration. Both are same in this case because mass is 1. So what I want to do is I want to increase the velocity by the acceleration. So this dot Vx plus equals to this dot Fx. Then this dot Vy plus equals to this dot Fy. And then I want the locations to be updated also. So x should be updated by Vx and y should be updated by what? Vy. So this dot Vy. Yeah. And then we also have to check the max velocity is not exceeded or something like that. So if, let's say, this dot Vx is somehow greater than this dot Maxwell. If this happens, what we want to do? We want simply to be Vx to be equals to the Maxwell. So this dot Vx equals to this dot Maxwell. That's all. And otherwise, let's say for the negative value, what happens? So if this dot Vx is less than minus of this dot Maxwell, so this may also happen, right? So Vx is not greater, but when it comes to the negative value, it is lesser than the absolute value of Maxwell. Of I mean, you got my point. So in that case, this should be equals to minus of this dot Maxwell. Yeah, very simple stuff. And the same should be done for Vy also. So here I will change all the Vx with a Vy. So Vy. And now we have something. Let's see, we get something or not. So and as we can see, we have some interesting interaction. So what happens is when two particles get very close, they are basically repelling each other, and all the particles are vanishing because we are not checking that condition. Kind of an interesting behavior, but we need to update few more things. So we have to update one round world. So the world should be round. So how can we do that? Very simple. So if x is somehow greater than canvas dot width, if this thing happens, I want the x value, the particle should be teleported back to the starting point. So this should be 0. Or also, if the opposite happens, if x is somehow less than 0, so it is vanishing from the left end of the screen, then I want it to be teleported to the right end. So this dot x equals to canvas dot width. This is not a teleportation. Actually, this is how round world works. And same for y. So this dot y, if this is greater than canvas dot height, if this thing happens, I want this dot y to be 0. Also, if the opposite happens, if it is vanishing from the top, so if this dot else if this dot y is less than 0, if this thing happens, then I want this dot y to be equals to my canvas dot height. Now let's see what is happening. So very interesting behavior. Particles are coming close and they're repelling each other and they're moving here and there. Very, very interesting. Um, yeah, it's kind of like a Brownian motion. Uh, Only when they're very close, they are repelling. Yeah. But now what we want is we want attraction also. So when the particles are at a larger distance, we want attraction also. And as you can see, the particles are not really vanishing. Yeah. Okay. It's already very interesting. So yeah. So let's get back to our function and let's see what more we can add. So here we are checking the smaller distance here in this line. Now, if this is how this is happening, then we are doing this. But else if something else is happening. So what is that something else? That is if dist dot dist is greater than equal to my p1 dot radius times 5, it should be more than this, and it should be less than something huge. So if let's say dist dot dist is less than our total size is 150. No, total size is what, 500. So less than 150, let's say. In this case, we want an attractive force. So attractive force means we want Fx plus equals to F dot force x, and Fx plus this will be Fy plus equals to F dot force y. Now let's see what we get. So yeah, so the particles are trying to come close to each other and also they're repelling, and both of these combined is causing some sort of a weird motion. I don't know what these things are. So, but yeah, it's kind of confused particles as it looks like. So here, let me give a smaller radius to 3, and now let's see. Mm, okay, something is happening. Something is happening. Interesting, but this definitely doesn't look like cells. So let's see if we can try to make it more like cells. So what I want to do is I want to add some friction also. So right now all the particles will are determined by how much force and velocity they have, but the particles do not slow down on their own. So I want some universal friction. So let me give an universal friction. Universal friction. Let me give it as 0.005. And what this will do is it will slow down the particles. So let me apply that also. I'll apply it after the Maxwell. So this is my universal friction. So if let's say this dot Vx is greater than equal to my universal friction, in that case what I want to do is I want the Vx to slow down by what? By the universal friction. Now else if my this dot Vx is let's say less than equal to minus of universal friction, that is in the opposite direction, I want this dot Vx plus equals to universal friction. Or otherwise, that is the other situations where the value of Vx is actually very small. It is less than universal friction in the positive side and more than in the negative side. In that case, the Vx should actually be 0. Lesser than the friction, I'm just making it 0. Now let's do it for the y also. We'll copy this one and keep it here. And let's change all the Vx to Vy. And now let's see we get something interesting or not. So yeah, so the particles are coming more close to each other. Yeah, yes, um, but I'm not sure. It's coming close and then it's going ahead again. What I think we can do is the max velocity is too high. It can be, I think, 1. It should be 1 because of the max velocity. I think yes, 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 yes. Yes. So now the particles are coming close and they are forming more like what we may call as cells. These are technically not cells, but yeah, at least the particles are coming close. So the max velocity was causing the issue. The repelled particles was moving too fast. Yeah. So now we can add some more particles to add some more spice into the scene. So What we can do is here we are adding particles. We are adding lots of red particles. So here, let's say I will also add yellow particles. So after the red, let me do a yellow, and the index will be 1 in this case. Now, yeah. So now all the particles are coming close, and we see something interesting. Let me keep the radius as 2. I think the smaller particles are better now. Yes. So we see some electrified particles, looks like. Yes. So some particles are with extreme speed, they are coming close to each other, and sometimes the velocity becomes high enough and they are thrown out. It looks like that. Yeah, it's kind of an interesting behavior. We will try to understand more of this. But for now, I want to give a different behavior to the YOLO particles. So right now, what happens? All particles attract each other, and at very close distance, they repel each other. But what I want for the YOLO particles is the YOLO particles should be attracted towards the red particles, but not the red particles. Something like that. I don't want them to behave similarly. So how can we do that? We can do that actually by doing this. So else if for every particle we will not do this thing. We will first of all check their color. So if let's say my p1 dot color is red, let's say, and my p2 dot color is let's say yellow. In that case, I want one kind of behavior. It should be and like this, and I want one kind of behavior. Else if let's say the opposite. So p1 dot color is yellow and p2 dot color is red. In that case, I want another kind of behavior, and for the all the remaining cases, that is red, red, and yellow, yellow, I want this. So what I want for the first case? So for the first case, the first particle is red and the second particle is yellow. So the red particle should repel the yellow particles. That is what we want. So fx minus equals to, let's say, f dot force x, and fy minus equals to f dot force y. So red particles will repel yellow particles. But for the yellow particles, I want to be strongly attracted to the red particles. So fx plus equals to f dot force x times 10, let's say, and fy plus equals to f dot force x force y times 10. So if you think about it, here we are multiplying by 10, and here the value of g is already 10. So here it is actually 100 times impact. So let's see. So yeah, so the yellow particles are chasing the red particles, it looks like, and I don't know if this is anyway living or what. Doesn't look like that. Doesn't look like that. Hmm. What we can do is, I think we can lessen the number to 5. Now let's see once again. Again, they will chase, but do they form interesting structures or not? Is what we would like to see. So yellow particles are interacting with each other, and they are also chasing the red ones. Um, hmm. Okay, so this one is kind of looking like a cell already. Yes, yes, yes. So the yellows attack the reds. Yeah. So it's like very small microscopic particles are interacting with each other to form something interesting. So they're trying to form cells here, as we can see, but I think they're not very successful. Yeah. So now doing these things in this sort of a fashion is not that good. What we can do instead is use one array, and that array can be named as interaction matrix. And in the interaction matrix, I want uh, the the names, basically the indices of the particles. So for example, let's say I have a 2 cross 2 for now. So it will be 1 comma minus 1, and then it will be 1 comma 5. If we have a 3 cross 3, let's say we also have a green or something like that, it will be, for now, let's just keep it 1 1 1. So 1 1 1. If we just add another green soup, let's see. Here we have a green also. and the green particles, in this case, are all attracted to each other. So green. Now let's see. Hmm. So I definitely didn't plan this behavior, but something interesting is cooking up over here, right? And here also. Okay. So the green particles are actually obstructing the yellow particles, and we have something like a cell kind of thing forming here, right? Very interesting behavior. I think this green color is not that strong. So the number two was green. Instead of green, if we can give a light green, maybe this will look much better. Hmm. Yeah. So very interesting behavior over here, right? So green and yellow particles will interact similarly, but when the yellow particles are close to red particles, something else will happen. So I think I can increase the factor for the yellow. Let's make it 10 and let's see. So the best way to do this thing is actually create some sort of an UI over here, and whoever is a user, they can change by themselves. And that will, I believe that will be much better, and we can have a lot of interesting things over here. So yeah, folks, I would like to keep the video up to this only. We will do a lot more things with these particles and a lot of simulations. We'll see how we can create some beautiful ecosystem. And yeah, that's it for this, folks. And I will see you soon with something very interesting very soon.